StreamDiffusion, a pipeline-level solution for real-time interactive generation. We introduce StreamDiffusion, a real-time diffusion pipeline designed for interactive image generation. Existing diffusion models are adept at creating images from text or image prompts, yet they often fall short in real-time interaction. This limitation becomes particularly evident in scenarios involving continuous input, such as metaverse, live video streaming, and broadcasting, where high throughput is imperative. To address this, we present a novel approach that transforms the original sequential denoising into the batching denoising process. StreamBatch eliminates the conventional wait and interact approach and enables fluid and high-throughput streams. To handle the frequency disparity between data input and model throughput, we design a novel input-output queue for parallelizing the streaming process. Moreover, the existing diffusion pipeline uses classifier-free guidance, CFG, which requires additional U-Net computation. To mitigate the redundant computations, we propose a novel residual classifier-free guidance, RCFG algorithm, that reduces the number of negative conditional denoising steps to only 1 or even 0. Besides, we introduce a stochastic similarity filter, SSF, to optimize power consumption. Our StreamBatch achieves around 1.5 times speedup compared to the sequential denoising method at different denoising levels. The proposed RCFG leads to speeds up to 2.05 times higher than the conventional CFG. Combining the proposed strategies and existing mature acceleration tools makes the image-to-image generation achieve up to 91.07 frames per second on one RTX 4090, improving the throughputs of auto-pipeline developed by diffusers over 59.56 times. Furthermore, our proposed StreamDiffusion also significantly reduces the energy consumption by 2.39 times on one RTX 3060 and 1.99 times on one RTX 4090, respectively. PowerInfer, fast large language model, serving with a consumer-grade GPU. This paper introduces PowerInfer, a high-speed large language model LLM inference engine on a personal computer, PC, equipped with a single consumer-grade GPU. The key underlying the design of PowerInfer is exploiting the high locality inherent in LLM inference, characterized by a power law distribution in neuron activation. This distribution indicates that a small subset of neurons, termed hot neurons, are consistently activated across inputs, while the majority, cold neurons, vary based on specific inputs. PowerInfer exploits such an insight to design a GPU-CPU hybrid inference engine. Hot activated neurons are preloaded onto the GPU for fast access, while cold activated neurons are computed on the CPU, thus significantly reducing GPU memory demands and CPU-GPU data transfers. PowerInfer further integrates adaptive predictors and neuron-aware sparse operators, optimizing the efficiency of neuron activation and computational sparsity. Evaluation shows that PowerInfer attains an average token generation rate of 13.20 tokens per second, with a peak of 29.08 tokens per second, across various LLMs, including OPT175B, on a single NVIDIA RTX 4090 GPU, only 18% lower than that achieved by a top-tier server-grade A100 GPU. This significantly outperforms Llama.ppp by up to 11.69 times, while retaining model accuracy. Generative multimodal models are in-context learners. The human ability to easily solve multimodal tasks in context, that is, with only a few demonstrations or simple instructions, is what current multimodal systems have largely struggled to imitate. In this work, we demonstrate that the task-agnostic, in-context learning capabilities of large multimodal models can be significantly enhanced by effective scaling up. We introduce EMU2, a generative multimodal model with 37 billion parameters, trained on large-scale multimodal sequences with a unified autoregressive objective. EMU2 exhibits strong multimodal in-context learning abilities. even emerging to solve tasks that require on-the-fly reasoning, such as visual prompting and object-grounded generation. The model sets a new record on multiple multimodal understanding tasks in few-shot settings. When instruction tuned to follow specific instructions, EMU2 further achieves new state-of-the-art on challenging tasks such as question-answering benchmarks for large multimodal models and open-ended subject-driven generation. These achievements demonstrate that EMU2 can serve as a base model and general-purpose interface for a wide range of multimodal tasks. Code and models are publicly available to facilitate future research. InstructVideo, instructing video diffusion models with human feedback. Diffusion models have emerged as the de facto paradigm for video generation. However, their reliance on web-scale data of varied quality often yields results that are visually unappealing and misaligned with the textual prompts. To tackle this problem, we propose InstructVideo to instruct text-to-video diffusion models with human feedback by reward fine-tuning. InstructVideo has two key ingredients. 1. To ameliorate the cost of reward fine-tuning induced by generating through the full DDIM sampling chain, we recast reward fine-tuning as editing. By leveraging the diffusion process to corrupt a sampled video, InstructVideo requires only partial inference of the DDIM sampling chain, reducing fine-tuning cost while improving fine-tuning efficiency. 2. To mitigate the absence of a dedicated video reward model for human preferences, we repurpose established image reward models, for example, HPSv2. To this end, we propose segmental video reward, a mechanism to provide reward signals based on segmental sparse sampling, and temporally attenuated reward, a method that mitigates temporal modeling degradation during fine-tuning. Extensive experiments, both qualitative and quantitative, validate the practicality and efficacy of using image reward models in InstructVideo, significantly enhancing the visual quality of generated videos without compromising generalization capabilities. Code and models will be made publicly available at the project's website. Cached transformers, improving transformers with differentiable memory cache. This work introduces a new transformer model called Cached Transformer, which uses Gated Recurrent Cached (GRC) attention to extend the self-attention mechanism with a differentiable memory cache of tokens. GRC attention enables attending to both past and current tokens, increasing the receptive field of attention and allowing for exploring long-range dependencies. By utilizing a recurrent gating unit to continuously update the cache, our model achieves significant advancements in 6 language and vision tasks, including language modeling, machine translation, list ops, image classification, object detection, and instance segmentation. Furthermore, our approach surpasses previous memory-based techniques in tasks such as language modeling and displays the ability to be applied to a broader range of situations. SpecNeRF, Gaussian directional encoding for specular reflections. Neural radiance fields have achieved remarkable performance in modeling the appearance of 3D scenes. However, existing approaches still struggle with the view-dependent appearance of glossy surfaces, especially under complex lighting of indoor environments. Unlike existing methods, which typically assume distant lighting like an environment map, we propose a learnable Gaussian directional encoding to better model the view-dependent effects under near-field lighting conditions. Importantly, our new directional encoding captures the spatially varying nature of near-field lighting and emulates the behavior of pre-filtered environment maps. As a result, it enables the efficient evaluation of pre-convolved specular color at any 3D location, with varying roughness coefficients. We further introduce a data-driven geometry prior that helps alleviate the shape-radiance ambiguity in reflection modeling. We show that our Gaussian directional encoding and geometry prior significantly improve the modeling of challenging specular reflections in neural radiance fields, which helps decompose appearance into more physically meaningful components. Zero-shot metric depth with a field-of-view condition diffusion model. While methods for monocular depth estimation have made significant strides on standard benchmarks, zero-shot metric depth estimation remains unsolved. Challenges include the joint modeling of indoor and outdoor scenes, which often exhibit significantly different distributions of RGB and depth, and the depth scale ambiguity due to unknown camera intrinsics. Recent work has proposed specialized multi-head architectures for jointly modeling indoor and outdoor scenes. In contrast, we advocate a generic task-agnostic diffusion model with several advancements such as log-scale depth parameterization to enable joint modeling of indoor and outdoor scenes, conditioning on the field of view, FOV, to handle scale ambiguity, and synthetically augmenting FOV during training to generalize beyond the limited camera intrinsics in training datasets. Furthermore, by employing a more diverse training mixture than is common and an efficient diffusion parameterization, our method, DMD, diffusion for metric depth, achieves a 25% reduction in relative error, REL, on zero-shot indoor and 33% reduction on zero-shot outdoor datasets over the current state-of-the-art, using only a small number of denoising steps. For an overview, visit the project's website. MaskINT, video editing via interpolative non-autoregressive mask transformers. Recent advances in generative AI have significantly enhanced image and video editing, particularly in the context of text prompt control. State-of-the-art approaches predominantly rely on diffusion models to accomplish these tasks. However, the computational demands of diffusion-based methods are substantial, often necessitating large-scale paired datasets for training, and therefore challenging the deployment in practical applications. This study addresses this challenge by breaking down the text-based video editing process into two separate stages. In the first stage, we leverage an existing text-to-image diffusion model to simultaneously edit a few keyframes without additional fine-tuning. In the second stage, we introduce an efficient model called MaskINT, which is built on non-autoregressive masked generative transformers and specializes in frame interpolation between the keyframes, benefiting from structural guidance provided by intermediate frames. Our comprehensive set of experiments illustrates the efficacy and efficiency of MaskINT when compared to other diffusion-based methodologies. This research offers a practical solution for text-based video editing and showcases the potential of non-autoregressive, masked generative transformers in this domain. Repaint 123, fast and high quality. One image to 3D generation with progressive controllable 2D repainting. Recent one-image to 3D generation methods commonly adopt score distillation sampling, SDS. Despite the impressive results, there are multiple deficiencies including multi-view inconsistency, oversaturated and oversmoothed textures, as well as the slow generation speed. To address these deficiencies, we present Repaint 123 to alleviate multi-view bias, as well as texture degradation, and speed up the generation process. The core idea is to combine the powerful image generation capability of the 2D diffusion model and the texture alignment ability of the repainting strategy for generating high-quality multi-view images with consistency. We further propose visibility-aware adaptive repainting strength for overlap regions to enhance the generated image quality in the repainting process. The generated high-quality and multi-view consistent images enable the use of simple mean square error (MSE) loss for fast 3D content generation. We conduct extensive experiments and show that our method has a superior ability to generate high-quality 3D content with multi-view consistency and fine textures in 2 minutes from scratch. Code is at the project's website. RadEdit. Stress testing biomedical vision models via diffusion image editing. Biomedical imaging datasets are often small and biased, meaning that real-world performance of predictive models can be substantially lower than expected from internal testing. This work proposes using generative image editing to simulate dataset shifts and diagnose failure modes of biomedical vision models. This can be used in advance of deployment to assess readiness, potentially reducing cost and patient harm. Existing editing methods can produce undesirable changes, with spurious correlations learned due to the co-occurrence of disease and treatment interventions, limiting practical applicability. To address this, we train a text-to-image diffusion model on multiple chest X-ray datasets and introduce a new editing method, RadEdit, that uses multiple masks, if present, to constrain changes and ensure consistency in the edited images. We consider 3 types of dataset shifts: acquisition shift, manifestation shift, and population shift, and demonstrate that our approach can diagnose failures and quantify model robustness without additional data collection, complementing more qualitative tools for explainable AI. Splatter image, ultra-fast single-view 3D reconstruction. We introduce the splatter image, an ultra-fast approach for monocular 3-dimensional object reconstruction, which operates at 38 frames per second. Splatter image is based on Gaussian splatting, which has recently brought real-time rendering, fast training, and excellent scaling to multi-view reconstruction. For the first time, we apply Gaussian splatting in a monocular reconstruction setting. Our approach is learning-based, and at test time, reconstruction only requires the feed-forward evaluation of a neural network. The main innovation of splatter image is the surprisingly straightforward design. It uses a 2-dimensional image-to-image network to map the input image to one 3-dimensional Gaussian per pixel. The resulting Gaussians thus have the form of an image, the splatter image. We further extend the method to incorporate more than one image as input, which we do by adding cross-view attention. Owing to the speed of the renderer, 588 frames per second, we can use a single graphics processing unit for training while generating entire images at each iteration in order to optimize perceptual metrics like LPI-PS. On standard benchmarks, we demonstrate not only fast reconstruction, but also better results than recent and much more expensive baselines in terms of peak signal-to-noise ratio, LPI-PS, and other metrics. Mini-GPTs, efficient large language models through contextual pruning. In AI research, the optimization of large language models, LLMs, remains a significant challenge, crucial for advancing the field's practical applications and sustainability. Building upon the foundational work of Professor Song Han's lab at MIT, this paper introduces a novel approach in developing mini-GPTs via contextual pruning. Our methodology strategically prunes the computational architecture of traditional LLMs like Phi 1.5, focusing on retaining core functionalities while drastically reducing model sizes. We employ the technique across diverse and complex datasets, including US law, medical Q&A, Skyrim dialogue, English-Taiwanese translation, and economics articles. The results underscore the efficiency and effectiveness of contextual pruning, not merely as a theoretical concept, but as a practical tool in developing domain-specific, resource-efficient LLMs. Contextual pruning is a promising method for building domain-specific LLMs, and this research is a building block towards future development with more hardware compute, refined fine-tuning, and quantization. Model-based control with sparse neural dynamics. Learning predictive models from observations using deep neural networks, DNNs, is a promising new approach to many real-world planning and control problems. However, common DNNs are too unstructured for effective planning, and current control methods typically rely on extensive sampling or local gradient descent. In this paper, we propose a new framework for integrated model learning and predictive control that is amenable to efficient optimization algorithms. Specifically, we start with a rectified linear unit, ReLU neural model of the system dynamics, and with minimal losses in prediction accuracy, we gradually sparsify it by removing redundant neurons. This discrete sparsification process is approximated as a continuous problem, enabling an end-to-end optimization of both the model architecture and the weight parameters. The sparsified model is subsequently used by a mixed-integer predictive controller, which represents the neuron activations as binary variables and employs efficient branch and bound algorithms. Our framework is applicable to a wide variety of DNNs, from simple multi-layer perceptrons to complex graph neural dynamics. It can efficiently handle tasks involving complicated contact dynamics, such as object pushing, compositional object sorting, and manipulation of deformable objects. Numerical and hardware experiments show that, despite the aggressive sparsification, our framework can deliver better closed-loop performance than existing state-of-the-art methods. Adaptive guidance, training-free acceleration of conditional diffusion models. This paper presents a comprehensive study on the role of classifier-free guidance, CFG, in text-conditioned diffusion models from the perspective of inference efficiency. In particular, we relax the default choice of applying CFG in all diffusion steps, and instead search for efficient guidance policies. We formulate the discovery of such policies in the Differentiable Neural Architecture search framework. Our findings suggest that the denoising steps proposed by CFG become increasingly aligned with simple conditional steps, which renders the extra neural network evaluation of CFG redundant, especially in the second half of the denoising process. Building upon this insight, we propose adaptive guidance, AG, an efficient variant of CFG that adaptively omits network evaluations when the denoising process displays convergence. Our experiments demonstrate that AG preserves CFG's image quality while reducing computation by 25%. Thus, AG constitutes a plug-and-play alternative to guidance distillation, achieving 50% of the speed-ups of the latter, while being training-free and retaining the capacity to handle negative prompts. Finally, we uncover further redundancies of CFG in the first half of the diffusion process, showing that entire neural function evaluations can be replaced by simple affine transformations of past score estimates. This method, termed linear AG, offers even cheaper inference at the cost of deviating from the baseline model. Our findings provide insights into the efficiency of the conditional denoising process that contribute to more practical and swift deployment of text-conditioned diffusion models. UniSDF, Unifying Neural Representations for High-Fidelity 3D, Reconstruction of Complex Scenes with Reflections. Neural 3D scene representations have shown great potential for 3D reconstruction from 2D images. However, reconstructing real-world captures of complex scenes still remains a challenge. Existing generic 3D reconstruction methods often struggle to represent fine geometric details and do not adequately model reflective surfaces of large-scale scenes. Techniques that explicitly focus on reflective surfaces can model complex and detailed reflections by exploiting better reflection parameterizations. However, we observe that these methods are often not robust in real unbounded scenarios where non-reflective as well as reflective components are present. In this work, we propose UniSDF, a general-purpose 3D reconstruction method that can reconstruct large complex scenes with reflections. We investigate both view-based as well as reflection-based color prediction parameterization techniques and find that explicitly blending these representations in 3D space enables reconstruction of surfaces that are more geometrically accurate, especially for reflective surfaces. We further combine this representation with a multi-resolution grid backbone that is trained in a coarse-to-fine manner, enabling faster reconstructions than prior methods. Extensive experiments on object-level datasets, DTU, Shiny Blender, as well as unbounded datasets. MIPNERF 360 and RefNeRF Real demonstrate that our method is able to robustly reconstruct complex large-scale scenes with fine details and reflective surfaces. Please see our project page at the project's website.